Okay, hello everyone. Welcome to our online course in the classical theory of minimal and constant mean curvature surfaces. I would like to actually begin by giving a lightning introduction to differential geometry. Okay. So I want to begin by giving you some references. There are 3 books. There's one which is an introduction to topological manifolds. There's an introduction to smooth manifolds. And there's a 3rd book called Riemannian manifolds. And introduction to curvature. And these are all written by John M. Lee. They're all excellent books, and they will all give you many more details than I can provide here. I want to give you just some background. So I want to begin with a definition. An n-dimensional smooth manifold is a second countable Hausdorff topological space with an atlas of coordinate charts. So what does this mean? Let's isolate each of these terms. Second countable means that any topological basis, any basis for the topology contains a countable subbasis. This is a technical assumption. It means that anytime you want to cover your manifold with a collection of open sets, you are always allowed to choose a countable cover. Hausdorff means we can separate points. So what does this mean that you can separate points? It means that for any pair of points, pair of distinct points in my manifold, there exist disjoint open sets. Let's call them UP and UQ, such that P lies inside UP, Q lies inside UQ, and saying once more that they're disjoint, the intersection between these 2 open sets is empty. The last condition, the atlas of charts, is really the most important. So this says that there exists a covering let's call this covering U alpha of M with associated open sets, let's call them U alpha tilde, lying in Rn. And mappings phi alpha mapping U alpha tilde to U alpha. So these I want to be homeomorphisms. Moreover, I want to say something about the smooth structure sorry, let's write this as phi beta inverse composed phi alpha. Whenever this intersection of open sets in Euclidean space is non-empty, I can compose my coordinate chart. So first I want to map from my set in Euclidean space to my manifold. And then I want to map back from my manifold into Euclidean space. I'm going to map forward to the manifold by phi alpha and backward to Euclidean space by the inverse of phi beta. And I want to require that this map here is a diffeomorphism onto its image. So what does this mean? This means that once I have this collection of coordinate charts, this gives local smooth coordinates near any point on my manifold. And another way to say this is just to say that a manifold and n-dimensional manifold looks locally like a small neighborhood in n-dimensional Euclidean space. And a large part of differential geometry, Riemannian geometry, all of these fields, a large part of this study is trying to determine to what extent looks like actually holds. Does your manifold look like Euclidean space on small scales only to the level of its differentiable structure? Does it actually look like Euclidean space on small scales in terms of distances, in terms of angles, in terms of how curves bend, anything like that? A lot of differential geometry is really understanding to what extent something locally looks like Euclidean space. So this is an important concept. I want to say one or two words about some other categories. A topological manifold only requires that the each phi alpha is a homeomorphism. And you can reduce the regularity. So for instance, a CK manifold requires that these transition maps I wrote down before are CK diffeomorphisms. So it makes sense to try to lower the regularity. It makes sense to ask for real analytics, so you can pose the same definition in the real analytic category. Or over the complex numbers instead of the real numbers. This means that your transition functions, your coordinate functions, are now required to have derivatives, have complex derivatives. So all of these different notions are very different. Topological manifold and manifolds of class CK, that's obviously a weaker condition than smooth manifold. Real analytic is obviously stronger condition. This is actually a much stronger condition. And the theory of real analytical manifolds is a little bit peculiar. One of the reasons it's a little bit peculiar, for instance, is that one cannot construct a partition of unity in the real analytic category. And also complex manifolds, the theory of complex manifolds is very, very different from this theory of real manifolds. You can see that by, you can see the fact that these two are very different just by understanding the difference between a function to have a real valued function to be differentiable and a complex valued function to be differentiable. Those two notions are vastly different. So this is some basic definition. Now, of course, once I have this, I can make sense of, so with my smooth atlas of charts, I can now makes sense of things like smooth functions. By saying that my function f is smooth precisely when the precomposition of f with any coordinate chart, any local coordinate chart is smooth. I can make sense of and I can, if I have two smooth manifolds, I can make sense of a smooth mapping between these two spaces. So I might have some capital F mapping M to N. And now I can make sense of this mapping is now smooth precisely if maybe I'll call them phi hat beta inverse composed F composed phi alpha. So what have I done here? I've taken my coordinate charts phi alphas on M, and I have some other family of coordinate charts phi hat betas on N. And now I can look at the pre and post composition. Now this is a mapping from open sets in Euclidean spaces, and I know what it means to say that this composition is smooth. So if this is smooth for each choice of my possible coordinate charts, which makes sense, then I say that my mapping F is smooth. So an important case to consider is the case of curves. So I might draw a picture here. I might have something like here's my manifold. And I might have some mapping gamma from an interval into my manifold that gives me some curve that might wind around between these 2 points. If I choose some point on the curve, let's call this point here P, I can now associate a tangent vector to the curve at this point, gamma dot, at some time let's say times 0, this gives me a vector. And now this gives me a way to differentiate functions. So I can write down, so I observe that I can observe that now this derivative by the chain rule, so this is by the chain rule, this derivative really only depends on the initial point and initial direction, the initial tangent vector of this curve. So formally, I can define the tangent space as an equivalence class of curves. And when are two curves equivalent, I say that the curve gamma is equivalent to the curve sigma precisely when the initial points coincide and the derivatives at 0 coincide. So this basically gives you a way to measure tangent vectors, and you should think of this derivative, and so we can identify, we can call this equivalence class X based at the point P. So this is some equivalence class of curves. And then we can say that X acting on a function is equal to the derivative at t is equal to 0 of f composed with gamma, where gamma is a representative curve. And by our definition, this derivative here, which we have evaluated, does not depend on which representative we choose. So this. So this all looks very formal and perhaps a little bit confusing. And in practical terms, one usually does not use this. Sometimes one uses this formulation of what the tangent space is at a point, but usually one uses the local definition in terms of coordinate charts. So locally, if phi alpha if my phi alpha is a coordinate chart, I should say that the how should you think about this? You should think about this as saying that locally, I've now coordinatized my open set U alpha, so I may as well think about this as an open set in Euclidean space. And at any point of this open set in Euclidean space, I have all of these tangent vectors, which are just the direction vectors, just the standard direction vectors in Euclidean space. And if I do this, I can write my tangent space at a point P is the span of these coordinate vector fields So what do I see here? I see that we have attached a vector space which is isomorphic to n-dimensional Euclidean space to each point P in M. Moreover, I see that these vector spaces are all tied or bundled together by the atlas of coordinate charts. And thus we have arrived at something very natural, which is an example of a vector bundle. So thus we have the tangent bundle TM. And what is this? This is now the union of all these individual tangent spaces. And remember that now they're all bundled together by the coordinate charts. You're used to thinking about this a little bit when you think about something like vector fields on the plane or vector fields in three-dimensional space. And when you think about vector fields in the plane, you must remember that So what is a vector field? A vector field is now a mapping from the plane to the plane across the plane, satisfying certain compatibility conditions. So an example to think about is just to make you a little bit more comfortable with all of this, you should think about vector fields in the plane. So you should think about vector fields in the plane as now a mapping from the plane to not just the plane, but the plane across the plane. And this guy here is the tangent bundle to R2. And it's going to satisfy the property X of P must have the form P comma XP. So what does this mean? This means that the vector as the vector field evaluated at the point P is now a two-dimensional vector sitting over the point P. And this is a sensible thing to write down. So tangent bundles and vector bundles in general might seem a little abstract, but they're nothing too much more complicated than manifolds themselves. So you should think about use again. I have some manifold associated to any point on my manifold. I have all these various tangent spaces, which you should think of in this picture as I'm given some surface attached to each point on the surface. I have all of these tangent planes. And if I want to put all of these tangent planes together in a coherent way, how do I do that? I use my coordinate atlas of charts, my atlas of coordinate charts that I have on my original surface. So the tangent bundle locally looks like U alpha crossed with Rn over the target space of each coordinate chart phi alpha. Right. So this now gives us a bundle, the tangent bundle I've associated to, so far I have a smooth manifold M, and this is equipped with an atlas of charts. From this smooth manifold of M, I naturally construct the tangent bundle. TM. And then I can talk about vector fields I can talk about vector fields on my manifold. So what is a vector field? A vector field now is what I'm going to call a smooth section of the tangent bundle. And what does this mean? This means that my vector field is a smooth mapping from the manifold to the tangent bundle such that at each point, x of p lies in the appropriate tangent space, which is the same thing as what we had drawn before in this special case of thinking about vector fields sitting over vector fields on the plane. Once I have this vector field, I can now associate to this a flow. I can associate a flow associated to my vector field. And how is this flow? What is this flow? This flow is going to be a diffeomorphism from some small interval about 0 crossed with m to m. And it's going to satisfy the condition that phi of 0p is p, and the derivative with respect to t evaluated at t is equal to 0 of phi of t p is xp. Given any vector field, this flow will exist for a short amount of time, at least, for instance, if the manifold is compact or if the vector field is bounded. And the existence and uniqueness of the flow is given by standard I should say short time. The existence and uniqueness of this flow, at least for a short amount of time, is given by standard ODE theory. Flows don't always exist for all time. In some cases, they do. So for instance, if you have a compact manifold, the flow will always exist for all time. So how should you think of that? Again, let's draw our manifold here. And I might imagine my vector field as giving me a bunch of vectors spread out all over my manifold. And how do I imagine the flow? I pick a starting point for my flow. So maybe I want to start here. And then I trace a trajectory. So maybe my flow is going to loop around like that. And so on. Right. So this gives a well-defined sense of the flow of any vector field. And it gives you a way to move around on your surface. I want to mention another associated, mention another associated bundle. And what is the cotangent bundle? So this is given by the vector space sitting over each point in the cotangent bundle is the dual space to the tangent space. This is nothing more than the space of all real valued linear functions on TPM. And this cotangent bundle is tied together. It's bundled together in the same way that the tangent bundle is bundled together. Okay. All of these notions now give us a way to define things like derivatives of a function, the differential of a function, or a directional derivative of a function. So we can define so how do we define both of these things? How do we define directional derivatives of a function? How do we define differentials of a function? So we let f be some real valued function. Nice, smooth, real valued function, which we understand what that means. If I have a vector field, then the vector field acting on the function f is defined to be the derivative with respect to t, evaluated at t equals 0. Let me say this, evaluated at the point P of f of phi t p, where phi is the flow of x starting at P. I can define this more basically, which we've already really seen this definition. If I have a vector in my tangent space, I can say that xp acting on the function f is the derivative with respect to t, where t is equal to 0, of f composed gamma of t, where gamma is any curve representing the vector x. So I can say that as gamma of 0 is equal to p, gamma dot of 0 is equal to xp. So this is really the same. These two definitions coincide. I can also write down, so this is our notion of directional derivative. I can also write down our notion of differential by saying that df is now going to be a section of the cotangent bundle. And it's defined by df acting on the vector xp is x acting on the function f. So this gives a notion of all the derivatives in an appropriate sense. So the thing I want to point out here is that the correct invariant notion of a total derivative of this real valued function on my manifold does not live in the tangent bundle, it lives in the cotangent bundle. There is a notion of a gradient which is somehow dual to the differential of a function. So later we will see the notion of the gradient of a function, and we'll see that this really depends on choice of metric. Okay, for the moment, we stop there and we will continue momentarily.